Dave, this is kind of just my crazy idea. So this can be edited out. I'll say that out loud.
Yep.
So that if Andy is seeing this and he's like, nah, this is like a little bit derailing, then we can edit it, chop it off. But what I thought was really interesting and ties back to
I am Ivy Westerham, and I am located in Charlotte, North Carolina, and I am a teacher turned actuarial analyst. Today, we're going to be talking about the Wallis Product, which is an infinite series product. The Wallis Product is going to be every even number over every odd number. So we're looking at the ratio between even numbers and odd numbers. And as you'll notice, each even number is repeated and each odd number is repeated. So we're bouncing off that symmetry. So let's take a moment to think about if that symmetry wasn't there. So we have each even number twice, each odd number twice. If we didn't have that, if we just had the ratio of each even number over each odd integer, one below, so 2 over 1, 4 over 3, etc., all the way to infinity, that would blow up to infinity because we're multiplying numbers that are greater than 1. If we multiply an infinite number of numbers greater than 1, we're going to blow up to infinity. Opposite is true as well. So if we took the ratio of every even integer over every odd integer, where we have 2/3, so the odd integer is 1 above, now every ratio is less than 1. So if we're multiplying numbers that are less than 1, that is going to approach 0. So as we multiply those, it's going to get smaller and smaller and approach 0. So we blow up to infinity or we go down to 0. But with this Wallis product, we're kind of going to oscillate back and forth until we reach a number. So our goal today is to kind of explore how and why this happens and to think creatively about this problem. We're going to get a little creative and we're going to imagine the love story of Romeo and Juliet. Okay, so Romeo and Juliet are hoping to converge while Romeo travels in curves and Juliet is bound by straight lines.
Quick pause for a big picture. We're going to use two methods to calculate the Wallis product. Ivy is discussing Romeo's arc method, which measures distances between points that exactly match the Wallis product, so it is an exact method. Juliet uses a shortcut method that measures chord distances, which Hannah will explain in a moment. Both methods will eventually use a circle that we will split into evenly spaced points, and both methods will use allies called the friar and nurse. The yellow friar always resides on one of the points, and the red nurse always resides halfway between the friar and the next point. Because distances around a circle can be a challenge, Ivy will start with a straight line approach.
I want you to look at that ratio there. So we have the friar over the nurse. So the yellow is the friar, the red is the nurse. So right now we're traversing a straight path and we're looking at this ruler from 0 to 2. All right, our friar is our even number. It's going to split it right in the middle, split the ruler right at 1. And then our nurse is going to split between 1 and 2. So that is going to be at that 1.5 down there. Okay, so we have our visual. And stay with me, it'll start to make sense. So what we're going to do is we're going to go to the left with our numerator 1, and then with our denominator 1.5. So we have 1 over 1.5, but then we have to approach that symmetry. We have to do the other side where numerator remains the same, it's 1, and then the denominator is going to just be that 0.5. So we have 1 over 1.5 and 1 over 0.5. Now, that doesn't look very friendly for us right now. That's not a very friendly fraction. We want to have whole numbers, so we're going to multiply it by 2. And now we have the first two terms of our Wallis product. We have 2 over 1 times 2 over 3, which is 4/3. 1.3. So we still have our 1 over 1.5 and our 1 over 0.5. But now we're going to expand to our next two terms. So now we have a ruler from 0 to 4. we're going to split it in half at 2. So our numerator is 2 instead of 1 now. And then we're splitting that difference again to get our odd number in our denominator from 2 to 3, 2.5. Same approach. We're going to go 2 over 2.5 to the left and then 2 over 1.5 to the right. If we multiply those by 2, then we have the next two terms in our Wallis product. We have 2 over 1, 2 over 3, 4 over 3, 4 over 5. And as you can see, we're getting a little bit higher in our product. It's going up to 1.42. You might go, why are we doing this? What's going on? Okay, so stay with me. We're going to turn this straight line into a circle, which is going to be integral to our solving of this problem. Because we're going to start to notice some stuff. Okay, so we just took that ruler and we turned it into a circle. So now we'll note that our friar is at the base of that circle. And then our nurse is the midpoint on between the top and the bottom. So it's the exact same distance. We've just turned it into a circle. And once we do that, we'll start to notice some important things. So we'll notice that that friar is down at the base of the circle both times. So that friar stays in the same position. No matter how many ways we break up our problem, no matter how many in terms we get, that friar is still at the base. And then the nurse is getting closer and closer and closer to the friar. So we have the nurse is right here, the nurse comes closer, and then say we had n equals 12 terms, even closer. So the distance, we're imagining our circle, and we're noticing the symmetry there. We're noticing the positions. We're starting to pick up a visual of this problem and its relationship to a circle. And again, noting that this ruler concept, if we multiply all of our numbers by 2, then we have all of the terms of the Wallis product, which is quite interesting. Okay, so here we are. If we have our n equals 12, we're getting closer. We're getting closer to the friar, and our product is getting a little bit higher. We can travel through straight lines via chords, okay? So that's what we're going to do with the next method that Hannah's going to explain, and we're going to kind of expand off of these two methods and see if they converge and they cross paths. In order to calculate our chords, we're going to use signs. So we might, I don't know about you guys, but I haven't seen that in a while. So you might need a little refresher course on that. But luckily we have David, my coworker, to explain that concept to us.
My name is David Lozansky. I'm actually originally from Tucson, Arizona. I was recently living in Washington, but now I'm in Colorado. I guess I just like to jump all around the West Coast at the end of the day. I'm also an actuary. Seems to be a common theme here. I wonder why. I got acquainted with Ivy here, and she got me introduced to Dave, and I am just so happy and excited to be a part of this cool group. This image here might be very familiar to you. Even some of you non-mathy people may have even heard of the great phrase Sokotoa. These brilliant mathematicians defined these terms called sine, cosine, tangent, and we have this helpful moniker here where we remember if we have any angle in this picture here, I'm calling the angle theta, which is commonly used in math for an angle. If we take the sine of any angle, it's literally just the ratio of the opposite side. So if we're here, the opposite is this guy here, which I'm calling O, or you can think of it as the Y coordinate if you know Cartesian coordinates. So that's the opposite over the hypotenuse. And something really cool I want to say is that we're actually dealing with a circle that has a radius of 1. So because of that, our hypotenuse is the radius is exactly 1. And this is going to lead to some beautiful simplifications for the purposes later. So if we start with a tiny triangle here that's just a little bit away from the x-axis, you can see, and maybe some of you have even graphed the sine function before on your calculator, but you can see that the y coordinate of the sine function is the same as the y coordinate of this triangle on the unit circle. If I let this play out a little bit, we get to pi halves here, which some of you may know is 90 degrees. You can see our sine function reaches its maximum there, perfectly lining up with the y coordinate on the unit circle. And lastly, letting it go all the way to 180 degrees, or pi, our favorite number. We get this beautiful demonstration where we see on one hand, we have the perfect half of a circle, and the other, we have one perfect half period of sine. Sine is the y coordinate on the unit circle. And this is very important for what we're going to do in just a second.
You know, there's nothing about the Wallis product here, but this is teeing up this 2 times sine times the pi of f formula that's going to be part of what Hannah's going to be talking about. And what Hannah's going to be talking about is that chord length and how do we calculate that. And so now it's Hannah's turn. And Hannah, why don't you let us know who you are, and then how can we calculate that chord length?
Sure. Thanks, Dave. My name is Hannah Park. I am from Columbus, Ohio. But a fun fact about me, while we are filming this, I am traveling right now and currently in South Korea visiting my family. And so I've had lots of fun preparing for this today's presentation. Similar to Ivy, we will start with the fryer. And this n equals 4 being just 4 quadrants of a circle. This makes it very easy to measure distance. I'll go clockwise from fryer to point 3. Since this is a nice 90-degree angle, the distance between fryer to point 3 is, if you do the Pythagorean theorem, 1 plus 1, square root of that is square root of 2. And then to point 4, all the way across the circle, is the diameter. And so if you're looking at a unit circle with radius of 1, that distance is 2. And then by symmetry, if you're measuring the distance from the fryer to point 1, similar to what we created for point 3, that is square root of 2. What you'll notice that is, if you watch 3 Round 1 Blue, the result of this fryer shortcut is always going to be the number of points. In this case, we have 4 points, and the product of square root of 2 times square root of 2 is 4. So I always thought that was fascinating because we are looking at a simple case of 4, but if you set this number to be any number, hopefully even number, just because that will make it symmetric, but that will always just be the product of those lengths will always come out to be the number of points on that circle. David shared earlier in his presentation was how the chord length can be derived a little bit more broadly if you're not given a very easy triangle like a 45, 45, 90 here. You can always get a chord distance by measuring the angle and turning that into a fraction of a circle, and then using David's formula of 2 times sine of pi times that fraction. And even though we use our easy way of just doing Pythagorean theorem of 1, 1, and then square root of 2, because this is a right triangle, you can use that same formula. Let's say 2 times sine of, this is quarter of a circle, so pi over 4. And you should be able to get sine of pi over 4 is square root of 2 over 2. So multiplying that by 2, you get the same square root of 2 that you would get here. And same thing for this. This is 2, and if you remember David's sine graph, pi over 2 is where that peak is at 1, and then so multiplying 2 times 1, you would get the distance of 2. Now, where it gets really useful is when you get into a little bit more uncomfortable angles like pi over 8, and we're like, we didn't learn a triangle with pi over 8, or 45 degrees divided by 2 is 22.5 degrees, and nobody really memorizes or knows that value on top of their head. But you can say confidently, apply David's formula to say the chord length I can calculate, because this is now sliced of a quarter of circle by half again. So this is 1/8 of a circle. And so you can see that here, the chord length of that would be 2 times sine of pi over 8. And then this long distance here is 3/4 of a circle. And then so that chord length will be 3 pi over 8.
We are now ready to use our shortcut lemmas to unlock the Wallis product. To evaluate, we approximate arc distances with chord distances, and it's expressed as the friar's product divided by the nurse's product. But as n approaches infinity, the arc and chord distances approach each other. And given our usual setup of n equally spaced points, the friar's product chord to n-1 points is always n. The nurse's product chord to all evenly spaced n points is always 2. But because the nurse's product includes the extra chord to the friar, we divide out that extra distance. We can measure the arc distance between the nurse and friar by first recognizing the arc distance from the friar to the next point is the distance around the entire circle divided by n. Then the distance from the friar to the nurse is half that distance, or pi divided by n. And the adjustment requires dividing out the chord distance between the friar and nurse. But as n approaches infinity, the chord and arc distances merge together. Then we substitute this result into our formula to arrive at the infinite Wallis product equals pi over 2. It is amazing that two simple lemmas, combined with the infinite limit, unlock one of the most beautiful results in all of mathematics.
I want you to use your imagination to rotate the nurse circle counterclockwise by a little bit. Just dial your, like you're dialing a clock, to have this nurse and friar align. What you're gonna see is almost like a friar with n equals 8.
Okay, is Hannah's idea crazy? To set the stage, recall the friar's perspective. Put n equally spaced points on the unit circle and place the friar at any point. Multiply the chord lengths from the friar to the other n-1 points, and that product always equals n. Let's see this on a clock face with the friar resting at 6. For n equals 6, we connect the friar to the even hours. Multiply those distances, which we show in teal, and the product is 6. Let's park that result so it's tattooed in our mind. Now, double to n equals 12. Connect the friar to all 12 hours. Multiply those distances, both the evens and the odds, with the odds colored in purple, and the product is 12. And here is Hannah's clever move. The n equals 12 product is the product of both evens and odds, but the evens alone already multiply by 6 from our n equals 6 case. So the odd hour distances must multiply to 2 because 2 times 6 equals 12. Clearly, these odd hour targets are not evenly spaced from the friar's perspective. But watch what happens when we rotate those odd targets 1 hour clockwise. Now they land exactly on the even hours from the n equals 6 case that we see on the right. The only difference is that we're starting from 7 rather than 6. That is, from the nurse's position. And because the chord distances are just rotated, their product remains the same too. One simple rotation shows that the friar's lemma and the nurse's lemma are really the same fact, just seen from points shifted by a fixed angle, kind of like how cosine is just a shifted sine. And Hannah's idea works in general. From the friar's perspective, 2k equally spaced points produces a chord product 2k. And if we enumerate the points 1 to 2k from the friar, the k even number points are also equally spaced, so the distance product for the k points is k. And that means the distance product for the odd number points is 2k divided by k, or 2. And then simply shift these odd points to start from 1 rather than 0, and now they land on even number of points, which are the same k evenly spaced points that the friar uses for the n equals k case, proving lemma 2 that the nurse's chord product to all k points is always 2. And this constant factor 2 from the nurse's product is what makes the Wallis product converge to pi divided by that number 2. The geometry of chords and the symmetry of half steps around the circle encode that beautiful denominator 2.
Math, I feel like how math is like observed, like it's like it already exists, we're observing it, and we're observing it, we're noticing it as humans. Like these, like the Wallis product, he didn't invent anything, he noticed it.
Well,
Like none of these mathematicians are inventing, they're noticing, they're like uncovering.
Discovery.
right. It's not inventing,
Discovering.
it's discovering, yeah, because when you were talking, David, I was thinking about the fact that all those things you talked about, you know, if we put a time on it, you put whatever time you want on it, say 100,000 years ago, we didn't have humans, but did that still exist? I mean, did pi still, I mean, did the necessity of circumference versus radius and all these things you're talking about? Well, yeah, it did. You know, so, you know, oddly enough, about every celestial object is spherical. It kind of imposes itself on us. My name's Brian. I live in Hampton, Iowa, and you'll have to Google that. There's no reason for you to know where that is. And I'm probably the only one out here that likes philosophy a lot better than math. I used to be an actuary, but now I just play one on Zoom. It's mind-boggling that a bunch of, you know, integers multiplied together in fractions comes up with pi over 2. It's just like, I don't know. It's just, it seems like it imposes itself on us again. It's always been there, but we discovered it. Yeah.
You have this index set of rational numbers. They multiply out at the infinite set length, and at the end, voila, pops out pi over 2, a transcendental number, an irrational number, a mysterious and beautiful number. And that just, I think that is crazy. You know, it is amazing that we can even wrap our minds as humans around concepts like this, and that we can apply them, you know, and solve amazing things in physics and all of these other fields of study. You know, pi is everywhere. It's universal.
What's mind-boggling to me is we feel like there are so many like unknown things like amidst the things that we know, like fractions that we can number, and then there are irrational numbers like pi or e that we have names for, but there are so many irrational numbers that we don't even know how to call it because they're not named. And
I think the more you learn, the more questions you have. Like I have a couple questions that that you just start to get more curious. But I think something that I have learned is to not be afraid of not understanding something. Like if something looks intimidating to you, you don't have to understand it 100% even to enjoy it, to learn something, to grow from it. You just want to continue to be a lifelong learner.
And what does this mean to me? This is a piece of art to me. It was given to us for us to enjoy, kind of like a sunset or a rainbow. Those are things given to us to sit and enjoy. And so I look at that right side and I see lots of things. It's massive, it's big, it's beautiful, but I feel like I have to, I can get lost and sometimes feel dejected because I know so little. And doesn't matter if you're the smartest mathematician, you still know very little compared to all of math. But then we transfer to the left side of the equation, it's my left. But then we see pi, and pi is kind of like maybe this group right here. It's a small circle of friends that we get around and we share things, and we understand each other. So with that, do not be discouraged and keep on discovering.